Okay, so the next talk is by Gabriel Scherer, and he will be speaking on the subject of constructor unboxing, or how CPP decides a halting problem.
Okay, thank you. So this is work on a low-level data representation feature for the OCaml programming language that led to a theoretical question that I found surprising. So the feature was designed and suggested by Jeremy Yallop over there. Nicolas, Chataing was my master intern working on implementing it. I did some work with him and also on the theory side. And then Stephen gave a lot of excellent feedback that influenced the work in interesting ways. So first, let's talk about what's already available in OCaml without our work. So let's say you define a type ID that has a constructor ID carrying an int parameter. So maybe you have a list of size 1 whose first element is ID 42. Okay, and the constructors, this algebraic data type, they are used for the constructors are used for two things. The first is, well, they mediate between the type ID and int, which are different, and this is useful when you program. And they also, at runtime, let you know which case you are in when there are several cases. But here there is only one case, so maybe at runtime you don't need to know which case you are in. You are in the unique case. So since 2016, we support this unboxed annotation that says, well, at runtime, you don't need to care about ID. So in the source, you still write the same thing, but in the data representation, the ID constructor is erased. And you can give a sort of space cost model for ML data types, where to store a value, the constructors with parameters cost 2 words, and a constant like 42 and nil cost 1 word. So you can see that you are going to pay 4 words to store this instead of 6 if you remove the unbox annotation. And you could ask, well, why is it this unboxing not an automatic thing that happens? The answer is that would break foreign function code that produces value using directly low-level representation. So you cannot change the low-level representation without telling anyone. Okay, so this is already around. And then Jeremy said, well, you know, we only know how to do this when there is a single constructor or a record field with a single field, But maybe we could do better. So we could have several constructors, and maybe we could allow to unbox one or several of those. So here is the killer example, a big num type that is either a small integer, OCaml uses machine size integer, or a big number as implemented by the GMP library. And it's useful to have these two cases because GMP has still a fair amount of overhead, it's very fast, but still, compared to machine integers, it's slow. So as long as your computations stay within the bounds of the machine integer, you want to stay in the small case. But then, if you don't have this unbox annotation, allocating the small constructor and dereferencing its value costs a bit. So if you can allow user to unbox it, well, on a given micro benchmark, we saw a 20% time speed up. And then if you have a large program that is memory hungry, using less memory is going to be beneficial in more diffuse, interesting ways due to locality. Okay, disclaimer, for most programs in real life, you will not see any difference if you add unboxing annotations because functional runtimes are just very fast at allocating stuff and the reference is not that costly when you have good locality. So in most cases, it's not so useful, but in some cases, an expert programmer can add this unbox annotation to speed up the program. But then you cannot just unbox everything. So maybe you extend your type T with ID, and you add an error case, and that carries an error code that is also an integer. So if you allow to remove both the error and the ID constructor, then at runtime you see 42, you don't know which case you are in. So that's a problem. So if you try to do this, the compiler, the experimental version of the compiler that we worked on, will stop you and say this declaration is invalid. Some unbox annotations introduce overlapping representation. So how do you implement this static analysis? Well, we propose to do it in 2 steps. First, you design an abstraction of the set of values at a given type that we call head shapes. So this is a design choice that you make. You choose an approximation or an abstraction as a syntactic object. So you can think of this as abstract interpretation if you want. And then to check this declaration, you compute the head shapes of the unbox constructor, and you check that they are disjoint. And this abstraction that you design, you have to make trade-offs. So you could abstract all the types by just it's a type, and then you would reject all the unboxing constraints because two types have the same abstraction and they are not disjoint. So if you pick a more precise notion of shape, then you will allow more unboxing requests and you will make your user happy. But then what you have to teach them so that they can use your language becomes more complex because they need to understand what these head shapes are and what their meaning is. So there is a simplicity trade-off. And finally, portability. So if you give too much details in this abstraction about the low-level representation of your implementation of the language, maybe you will not be compatible with another implementation anymore. So in particular for OCaml, we want to find an abstraction that works well for the upstream bytecode and native compilers, but also for the JavaScript backend. And this approach could be used in other languages to support the feature. Any ML family language or could use the same approach. And they would pick their own specific abstraction. So then, okay, so we have this idea. How do you compute the head shape of a type to check? So here is an example. I have a type of n-ary trees, which are nodes of, a sequence of children and a value. So each child has a value attached to it, whatever. And then you have this type of sequences, which are either empty sequences or func that will on demand return you the first element of the sequence and the rest. And then you have some type foo that contains an integer tree with an unbox annotation. So to check that, the compiler needs to compute the shape of the data type in tree. So you say, oh, what's the shape of a tree? Oh, it has a single constructor that is unboxed. So the shape of that is actually the shape of the constructor argument. So you expand the definition, replacing alpha by int. And then, the shape of sec, that's either a nil constant constructor or the shape of a function. And this, simplified in our language of shape, you would say it's nil. The shape is an immediate value 0. And the function, let's say it's a block whose tag is closure tag. So that's easy. And that's easy, and what we did is to pick a definition and replace its formal parameter by its actual parameter. This is called beta reduction, okay? So actually what we did is to compute a normal form, head normal form, in, let's say, call by name. So in other words, you can reformulate this computation by first compute the head normal form of your type, and then it's easy to compute the shape from that. So you compute the head normal form of a type expression. This is nice. So you can represent this as a term in lambda calculus, okay, with flat rec. So above we have type declarations, and I'm reformulating them at the level of terms, okay? You can see above we use the WSML syntax where the parameter is on the left of the type parameters type, and below we use the standard lambda calculus syntax tree int. So this is just normalization in a lambda calculus with recursion. But of course, you can have recursive definitions of types, which translate to recursive term definitions that may not actually have a normal form, okay? So the problem is you don't want the OCaml compiler to loop indefinitely when you write a erroneous type definition. So how can you have it, compute the head shape but not loop indefinitely when there is no normal form? So this is the simply typed lambda calculus with just functions, no booleans, no sums, no integer, whatever. You have let rec, and actually we're in the first order fragment because in ML, the parameters of data types are not themselves used in function application in the definition. So quick show of hands. How many of you think that this, the problem of deciding termination in this fragment is decidable? And how many would say that is undecidable? I can give you a hint. So it's actually, the first order restriction does not matter. It's the same in the higher order case. Okay, so many people are sleeping and they don't want to use a hand, or they think it's dangerous to give. So the first thing we said is, well, maybe we can make the problem go away by forbidding cycles, but in fact we like recursive data types and we want to be able to unbox them, so this is not good enough. And then we said, okay, let's just reduce the type, and if you see the same types occurring twice in the reduction sequence, well, you are cycling and you stop. This is not good enough to prevent non-termination because you can use so-called non-regular recursive types, like bad A is bad of prod AA, and this, if you start from bad int, will reduce to an infinite sequence of types that are all different. Then you say, well, okay, the problem was the type is always different, but the bad head constructor is the same. It shows up again and again. So let's stop when the head constructor shows up twice. So the problem with that is that there are perfectly fine definitions like this. Identity of A is A, and foo is ID of ID int. Well, first you reduce foo, and you haven't seen any head constructor yet. So you reduce that to ID int, and you remember that you reduce foo. And then you reduce ID, so you get ID int, and you remember that you reduce foo and ID. And there, the algorithm stops you and say, well, you already reduced ID, so there might be a loop, stop. And this is not good enough. There are type declarations where this kind of pattern shows up in practice, and you don't want to reject them just because you should have used fuel instead of trying to be principled about this. Okay. So the last iteration of this ID is the one we used in the end. The idea is to track not just the head constructor that you expanded at the top level of the term, but for any sub-expression in the term. So I changed the example just a bit. So delay of A is ID A, and foo is delay of int. So you start with foo. Can I use function pointer? Yes. You start with foo. No. Okay, let's not do that. You start with foo, and then you go to delay of int. And these two terms, so the int as a subterm and delay of int as a subterm, they appeared in my term when I expanded foo. So I use the trace foo for both of them. And then you expand delay. So all the ID subterms that occurred when I expanded delay. So in their trace, I have foo and delay. But the foo int argument of the delay, it was already there before, so its trace does not change. So you get ID int with these traces, and then you reduce the application of ID, but ID does not create any new subterms. It's just returning its argument. So the argument has the same trace as before. And then you can reduce ID again, because in the trace of the ID int term, you never reduced ID yet, so you can reduce it again, and you get to a normal form. So this algorithm, it works in practice. It accepts all the examples that we wanted to accept. It rejects all the cycles that we thought of. So we were very happy with that. And we were hopeful that it was actually guaranteeing termination. And Stephen remarked that this is similar to the way an obscure algorithm from the 80s has been proposed to check termination of macro expansion in the C preprocessor. Okay. So we proved that this algorithm is sound, that it ensures termination, and it's complete in the first order fragment, which is the fragment we care about, in the sense that if it rejects an input, so if it stops before reaching a normal form, then actually there would have been a loop in the definition. So, okay, is this problem actually decidable, if we can have a sound and complete decision procedure? Answer is yes. So when you are surprised by something and you don't know why it is the case, you can ask types list about it. So I did that, and we got excellent replies by Pablo Barenbaum, Martin Leston, Gordon Plotkin, and Sylvain Salvati, who said, but this is a well-known thing. Simply typed angular calculus with just functions, and LETREC has decidable halting problem. Okay, so well-known by not me. Actually, there is a whole scientific community working on higher-order model checking, which are harder versions of this question. And there is a paper by Gordon published in 2022, but it says that it actually notes that were written 40 years before that explain that in a fairly readable and understandable way if you are not familiar with tree automata and MSO and whatever. Okay, so one thing that is interesting to be said about this is that we looked at, for example, the bound, the bound on the normal expansion that is implicit in the proof of Gordon, that is clearly explained. It's the height of a lattice, and we compare it to our algorithm. And in general, our algorithm reduces less before it stops and say, oh, there is a cycle. So it's more efficient on the first order fragment than, let's say, Plotkin's algorithm. And we don't really understand yet whether, well, there is a better algorithm that people already know in this community that coincides with ours, or maybe ours is specific to the first order case, or maybe we could sort of generalize it to a slightly more efficient high order algorithm. I'm done. Thank you.
Great. So we have time for questions. Caroline, there's one on this side.
I'm afraid I have a very simple, dumb question. So one thing I just didn't understand earlier on. So if you unbox a data type with two constructors, and you're saying you're allowed to do that if they're different types, they have different head shapes, how does the implementation then do that distinguishing without having a tag to look at in the runtime?
So the language of head shape that we picked has two properties. First, we can decide non-disjointness statically. And then the reason why two things are distinct is easily checkable at runtime, because the approximation that we use is basically, well, look at what's the header in the value, whatever. So the pattern matching compiler that has to make this choice at runtime can well, check disjointness dynamically by looking at this information.
Okay, so like an int and a float wouldn't be distinguishable or something like that.
So in upstream OCaml, yes, you can. In JavaScript OCaml, no, you cannot. So probably we will want to forbid you from forbid the unboxing checking from assuming that you can distinguish them to get portability.
Okay, awesome, thanks.
Thanks for the nice talk. So I was wondering if you could say a bit more about what types you can now actually represent unboxed and how that compares with other languages that do at least superficially similar looking things. Like Rust has all sorts of enum layout optimizations, and option bool can be stored in a single byte and things like that. And maybe that's something OCaml could already do before that. I'm not entirely sure there, but like what does this look like now?
Yeah. So there is a discussion in the paper about niche filling and whether you can see niche filling as an instance of this with a well-chosen abstraction. There is some related work by that was at ICFP on data layout description language that was instantiated with both OCaml and Rust, and that you might have heard of, and that is maybe going more in this direction. One thing I want to say is that no, OCaml does not let you unbox the option type because of this very compositional compilation approach with uniform representation and separate compilation. So we do not monomorphize or specialize aggressively. So that restricts a lot the things you can do. But this unboxing question is sort of orthogonal in the sense that if either you are in a language where you are more aggressive with your specialization, or you allow yourself, when you have a type parameter, to add sort of constraints about, oh, I assume that the shape of this parameter will be this and that, then you can unbox more. Okay, so they are sort of orthogonal.
We have maybe time for one short question, Neil.
So are the unboxed things all still one word? So if you unboxed a record, it would still be a pointer, or does it lay it out as multiple words?
No, you can only unbox if for variants if there is a single parameter, and for records if there is a single field. So in each time you have one word, yes. Because OCaml values goes back to the uniform representation, they always fit in one word.
Oh, okay, so that's to make polymorphism efficient. Okay.
Okay, let's thank Gabriel again.